All right, so let's finish up our discussion on metabolism, then we'll move on to some other stuff. Actually, yeah, this is, I guess, where we left off, sort of showing how morphine gets metabolized using glutathione. And it's a little weird because glutathione is a nucleophilic cofactor, and there's not really much we can do with a nucleophile to morphine. So the idea was that alcohol can be oxidized to a ketone, and then we can do a conjugate addition with glutathione and make this kind of product, which is then excreted. Or you can imagine a weird oxidation of the phenol to make a conjugated ketone, a diconjugated ketone, and then this is a Michael acceptor, and then glutathione attacks and kicks the electrons forward, and then you get a glutathione there. So it's kind of weird, but it shows, kind of the magic of P450, that it can deal with some cool stuff. All right. And so another thing about glutathione is not only are the glutathione conjugates excreted, but sometimes they degrade themselves to a different conjugate called N-acetylcysteine. And let's show an example. And this is something that might be called phase 3 metabolism. So phase 1 metabolism is like introduction of a functional group, oxidation or reduction or hydrolysis or something. Phase 2 is attachment of a conjugate like glutathione or sulfate. But then we may have this degradation process that we will call phase 3 metabolism. And so phase 3 metabolism, an example, is if we have an electrophile, and knowing that glutathione reacts with electrophiles, it'll attack the electrophile and form a conjugate. The enzyme that catalyzes this is glutathione S transferase, and then an enzyme will actually remove the glutamic acid portion that's conjugated to glutathione. So it cleaves this peptide bond. It's gamma glutamyl transpeptidase is the enzyme, and that is essentially a hydrolysis enzyme in this case. So it cleaves that bond, leaves the amine, and then we still have a glycine, and then another enzyme, cystenyl glycine dipeptidase, is a protease essentially, or a peptidase that cleaves this bond between the glycine and the cysteine, and that leaves you with the essentially cysteine, right? And then this cysteine conjugate can be acetylated using acetyl-CoA, which, remember, acetyl is the 2-carbon piece, and then CoA is the biological leaving group. So essentially it's like acetyl chloride or acetic anhydride, but a biological version. And that acetylates the nitrogen and gives you this N-acetylcysteine derivative, and that can be excreted. One interesting thing about this is that it actually preserves glycine and glutamic acid in your body, so you're not like kind of throwing away good amino acids. And they can be recycled into more glutathione or other proteins and things like that. Methyl conjugation is another phase 2 metabolic process that is maybe less common. Here's an example. So this is oxprenolol, which is a coronary vasodilator, and kind of through normal P450 mechanism, this isopropyl group will be cleaved. So P450 oxidizes the CH, and it's doing a standard oxidative dealkylation that you're familiar with. So oxidize the CH there, yeah. And then the oxygen swings in, kicks off, and gives you an amine. So you get a primary amine. Well, anyway, this is a detectable metabolite. And it's produced by the methylation of the amine, and this uses methyltransferase enzyme. And then remember, the cofactor for all methylation stuff is S-adenosylmethionine. So it's just like acetyl-CoA is the acetylation cofactor, and glutathione is the glutathionylation cofactor. S-adenosylmethionine, or SAM, is kind of like a methyl iodide, biological methyl iodide, which just methylates stuff. Okay, what's the mechanism, and kind of how is SAM produced? S-adenosylmethionine. It's pretty easy mechanism. So there's methionine, and essentially ATP comes in, which is adenosine triphosphate, and the sulfur kicks off all three phosphates: a PPI, which is a diphosphate, and PI, which is a single phosphate. And then essentially now you have methionine here attached to adenosine with no phosphates. And so this is S-adenosylmethionine. Anyway, so this is the methylation cofactor. And now whatever you're methylating with its lone pair and a methyltransferase enzyme reacts, attacks, kicks off sulfur, and then you're left with, I'm not sure what that would be called. It's no longer S-adenosylmethionine, but some other molecule, and then your methylated product. Okay. Acetylation. This is straightforward. We already kind of talked about this, but here's silistin. It's a dehydropeptidase inhibitor, so a protease inhibitor, and the reaction is acetylation. So it's a really simple reaction where we're essentially attacking acetyl-CoA. CoA is the good leaving group, a biological leaving group. The enzyme catalyzes this, and you get acetylation of the nitrogen. Methylation and acetylation are unique in that they actually enhance lipophilicity. So that's kind of weird, like, right? Because usually you think of metabolism as something that enhances polarity and maybe excretes things, and certainly glutathione attaches an amino acid that can be readily excreted. This looks like we're not making it more polar, we're actually making it more lipophilic. And so this is kind of counterintuitive, but what could be argued is that even though we're not enhancing its excretability directly, we are inactivating it. So that could be the sort of biological rationale for why a reaction like this happens. That we're inactivating an active drug. Okay, conclusion from the metabolism section. So phase 1 metabolism introduces or reveals functional groups to aid excretion. It's often oxidation, or as we've seen a couple times, oxidative dealkylation, reduction of like a ketone or a nitro or an azide, hydrolysis of an ester or amide. Phase 2 metabolism conjugates these small molecule cofactors to drugs, and that aids in excretion. So that could be glutathione or acetylation or methylation, things like that. Methylation and acetylation are unique in that they enhance the lipophilicity of a drug, which may reduce its excretion. They do probably cause inactivation of most drugs when you attach these other foreign groups on them. This book is really good, and also I think the Silverman book, which has a lot of examples of metabolism. This book on the right is, if you're going into drug discovery later in your career, it has a lot of examples of kind of preventing drug metabolism and dealing with ADME issues like toxicity, cell permeability, etc. So these two books collectively are really good. I think the third edition is the current one for this Silverman book, Organic Chemistry of Drug Design and Drug Action. All right, so we're kind of on to the next section, which I'm calling Introduction to Physicochemical Parameters and Chemical Informatics Tools. So what we're trying to do is, through this course, give you a broad perspective on the organic chemistry of drugs. We talked about synthesis and some things like metabolism and ADME principles, pharmacokinetics. I want to highlight some kind of cool, chemical informatics tools, which are basically computer tools that help us in drug discovery. And in order to do that, we also need to go into a couple more physicochemical parameters, which are kind of like constants that are helpful in understanding how drugs work. So let's get into it. This book is also useful for this section, and it talks about a lot of these drug-like properties and some of the parameters we'll be talking about. It's not an essential book to read, but if you're able to find a copy of this, it's definitely good one for your bookshelf for concepts like, drug-like properties, which is going to be a major thing that we can examine using computers, for example. Okay, so as of now, the agenda are these things: physicochemical properties. We're going to review oral drug absorption through the GI tract. Talk a little bit about aqueous solubility and these parameters called log P and C log P. Also something called polar surface area, PSA or TPSA. These two parameters, log P and PSA, are pretty critical when we're trying to evaluate if a drug is likely to absorb effectively as an oral drug, okay? Because oral drugs have specific requirements for it to pass through your GI tract. We're also going to talk about something called the Lipinski Rule of 5. So it's a rule-based system that kind of lets you evaluate the likelihood your drug will be orally bioavailable. There's also something called the Weber rules. So these are both kind of competing rules. Lipinski happens to be a pretty well-established one. It's also pretty easy to remember. So we'll show some examples of that. Then I'm kind of going to move into some computer tools, chemical informatics, or computational tools that, for one, let us figure out log P or C log P and also PSA, TPSA. We're also going to talk about something called SMILES. So SMILES is a computer representation of chemical structure. That's very, very common. You may have never seen it before, so it's good for us to talk about. We'll show how we can generate three-dimensional chemical structures pretty easily using the SMILES string. Also, we'll talk about the prediction of drug likeness, and this will be kind of using or determining some of these parameters from above. We're also going to talk about prediction of metabolism. That's really cool. We can predict what sort of metabolic pathways will happen for a drug that without even doing a metabolism study. I'm going to add more stuff later, but right now this is a good start. All right. Let's talk about physicochemical properties first and talk about oral drug absorption through the GI tract. Okay, so as we've talked about before, absorption of an orally administered drug requires passage through the stomach or small intestine. It can absorb in either the stomach or the small intestine. Interestingly, each stage has an increasing pH, and that can kind of affect the drug absorption. Okay, so when a drug is administered orally, it first passes through the esophagus, gets into the stomach, and then we have the small intestine, which is composed of the duodenum, the jejunum, and the ileum, which are kind of this sort of tubular passageway that eventually leads to the large intestine, which is basically the colon, and then eventually gets excreted. So usually oral drugs are either absorbed in the stomach or in the small intestine. Usually, the stomach is actually kind of not an ideal drug absorption location because the surface area is not very great, whereas the intestines have tons of surface area, so drugs can really absorb more readily there. As I mentioned, the pH increases from the stomach to the duodenum, to the jejunum, into the ileum, and that's going to potentially affect our drug absorption also. So this shows the pH and transit times of the different GI tract locations, and the stomach, of course, is an acidic environment. It actually kind of depends on if you're fasted or fed, but it's definitely acidic, and fasted is a little more acidic. And if you're fed, it's a little less acidic. But as you can see, the pH kind of increases from the stomach to the duodenum. Jejunum is pretty similar, and then the ileum is a little higher. A drug's protonation state can affect its ability to absorb, because the drug's got to be neutral for it to pass over a membrane, and these all contain membranes that would need to be passed for a drug to be absorbed. So for example, naproxen has a carboxylic acid with a pKa of about 4. What does that mean? Of course, that at lower pHs than 4, the molecule is going to be protonated, and at higher pHs than 4, it's going to be deprotonated. At pH 4 exactly, it's going to be half protonated and deprotonated, right? That's the meaning of pKa. So a drug with a carboxylic acid like this is most likely to be absorbed actually in the stomach, and because the pH is lower. And so it's a likely location for drug absorption. And a lot of these painkillers and NSAID drugs, the non-steroidal anti-inflammatory drugs, and like aspirin also, all have a carboxylic acid, and those would all be absorbed kind of in the stomach acidic environment. Whereas a drug like fluoxetine, Prozac, it's got an amine, and I'm showing it in its protonated form. There's a reason I'm doing that, because if I show it without the extra proton, like the normal neutral molecule, then we can't really show the pKa of it. The pKa is meaningful for an amine like this only when you show it in the protonated form, right? Because if I get rid of one proton and I show the other proton alone, its pKa is like 35. It's a very difficult proton to remove. Anyway, so when we're considering like an amine like this, you always show it with its extra proton on it, and then we show the pKa, which is roughly 9 or 10. Okay, so where is this likely to be absorbed? Well, in the acidic environment of the stomach, it's going to be completely protonated and less likely to passage through a stomach membrane. And even in the duodenum and jejunum, it's still going to be kind of protonated, because only at pH 10 would it be kind of half and half. So we're still fairly protonated in the duodenum and jejunum. In the ileum, it's starting to get a little less protonated, and so it might be a little more closer to neutral, and it's still not going to be perfectly absorbed. So a lot of this is still probably going to be just passed into the colon and excreted. And if we want to quantify the amount of neutral permeable drug molecule at a specific area of the GI tract, or like at a specific pH, we would use the Henderson-Hasselbalch equation. So this is you might have learned this, it's probably in Gen Chem, I guess. And there's kind of like two forms that we use. One is if you have a weak acid, which is kind of like naproxen with a carboxylic acid, pKa is 4. So pKa would go into here, and the pH would be set to maybe 2 or something like that. And this will determine the amount of A minus versus HA. And in this case, HA is the one we'd want. That would be the absorbed one. And again, at a lower than 4 pH, it'll be mostly protonated, yeah, right? So you could do the calculation for this. As a pharmacologist, you would do this kind of a calculation. We may or may not do it on a homework assignment, but it's a pretty simple calculation. And the pKa again is the pH at which 50% is ionized. Okay, so you could imagine that because the log of 1 is 0, right? So if the pH and the pKa are the same, so like let's say we're at pH 4, pKa is 4, log, the only time log would be 0 would be if this one, both of these are 1. So that kind of explains this result. For a weak base, and we could call this a weak base, also this amine, the equation is just slightly different. And what we're looking at here is B, there's B and BH plus. BH plus is going to be the protonated form. B is going to be the neutral form. And the B is the one you'd want to actually, that's the required one to be neutral, and which would transition through one of these membranes, or one of these organs. Okay, so passive diffusion through the GI tract requires a sufficiently lipophilic and neutral molecule. This kind of shows how it works, and this is a typical phospholipid bimembrane. And I mean, it's a very nonpolar environment. You have these long fatty chain fatty acids, and then there's it's a lipid, so there's a glycerol and a polar head group. But anyway, a drug needs to get through this. There's also like active transport and other methods that use proteins to help facilitate this process. But passive transport is a pretty big one for drugs, and it requires the drug to be neutral in order to transition through this environment. Okay, and for it to do this, it's got to, like, there's going to be solvent and water around the drug that needs to come off, and then it needs to kind of enter basically a greasy patch of membrane and make it all the way through, almost 50 angstroms from beginning to end, and to be absorbed in order to be actually effective as a drug. This is called passive diffusion. All right, so aqueous solubility, log P and C log P. What are these concepts? You may or may not have heard of these in your other classes. So it really refers to the ability of a drug or any organic molecule to dissolve in water, and it like the way we determine this, the classic method is kind of with a SEP funnel or some kind of thing like a SEP funnel. And we partition between N-octanol and water. That's just kind of the standard solvent. Why N-octanol? It's historical. I don't really know why N-octanol was chosen, but N-octanol does dissolve a lot of organic-y molecules. So our drug needs to be sufficiently soluble in the water and not be sucked into N-octanol. So P, when I say log P, well, what's P? P is the concentration of drug in octanol divided by concentration of drug in water. So a larger P will be more in octanol, and a smaller P would be more into water. And then we take a logarithm of this. So we take P and we take a logarithm of it. Okay. So for drugs, log P usually varies from like 0-ish for a highly polar drug, that's not like stuck in the water, to 7-ish, which is very greasy. And for an orally bioavailable drug, it's kind of somewhere in the middle, like 3 or 4 or something. Yeah. So why does solubility or lipophilicity matter in a drug? You may have never thought of that before. But yes, a drug needs to be somewhat aqueous soluble in order to operate in your body, because it needs to be able to dissolve in blood and in your biological fluids, in the cytoplasm, and things like that. and if it doesn't dissolve, it can't be active. So drugs need to be dissolved in aqueous solution, or more like biological solution, and they have to be somewhat polar to be dissolved in a mostly aqueous environment to be active. But at the same time, they also have to be sufficiently lipophilic, greasy, to pass through bilipid membranes. And like in the intestines or cell membranes to access a drug target. So it can't be so polar that it's just purely 100% aqueous soluble, because then it won't pass through membranes. Okay. A typical example of this is peptide drugs. I think we mentioned the HIV fusion inhibitor Fusion. You can Google that one, Fusion, F-U-Z-E-O-N, I think it was, or something like that. Fusion. Actually, I'm going to try something. I'm going to see if this works. I'm going to bring my browser over and see if I can get it. Let's see if this works. Fusion, Wikipedia. Yeah, this works. That's cool. Okay, so I can capture my browser. This is look at that. I don't know if you can see it. So it's a peptide. It's a huge peptide, right? This is an amazing HIV drug. It's an amazing HIV drug called Fusion, and this inhibits GP41, which was one of the HIV fusion proteins. I think I have a video of this on my iLearn page of how it works and how it inhibits HIV fusion. Anyway, as a big peptide, you would think, is this going to be aqueous soluble? And the answer is yes, it's totally going to be aqueous soluble. But could this be used as an orally bioavailable drug? The answer is no, because it's not going to be greasy enough to actually transition through membranes. If you take this orally, it would just be kicked right out of your body. So the way this drug works is it has to be intravenous. So it has to be administered intravenously. Okay, so that's a cool example. Any drugs that are incredibly polar or peptide-like are all IV drugs. One more example is vancomycin. Vancomycin. It's a pretty amazing molecule in terms of its chemical structure. It's one of the last line antibiotics. I mean, like if you have the worst bacterial infection in the world, this would be kind of like one of the like a Staphylococcus or a MRSA, methicillin-resistant Staphylococcus aureus, like a pretty serious bacterial infection. This would be one of your last line antibiotics. There's other ones kind of like this, but this is a very, very polar molecule with like these sugars on it and a lot of amino acids. Very, very polar, and this is not going to work orally. I think the only case where this is actually used as an oral drug, oral administered drug, antibiotic, is if you have an intestinal infection. So it would actually, you'd take it orally and it would go from your stomach into your intestines, and then it would treat the bacterial infection. So that's kind of interesting. But yes, so this you'd never take this like orally to treat like a bacterial infection inside your body. Okay, so as I was saying, drugs need to be sufficiently lipophilic to pass through bilipid membranes, and either in the intestines or in a cell membrane to access the drug target. Some drugs need additional lipophilicity if you're trying to pass the blood-brain barrier. Okay, so the blood-brain barrier is very greasy, so molecules that, neurologically active molecules may need to be a little more greasy. The other thing is that C log P, what's that? We have log P and C log P. C log P is simply log P, but determined by a computer program. So we don't actually have to get out of setphenol and octanol and water. We can actually kind of predict it by a computer program. And there's a lot of computer programs that do this. This is very, very convenient because we can do this on like thousands of molecules very rapidly. And most people nowadays, use C log P as a pretty good estimation of log P. Here and there, to get a really, really accurate reading, you would actually do this kind of experiment. Okay, so more on log P and C log P. C log P is incredibly convenient compared to doing a log P determination with a SEP funnel, or there's some microscale ways of doing it. But you may need to use HPLC or UV-Vis or some kind of analytical technique to determine how much is aqueous and how much is organic. And whereas a computer program, we can do this very rapidly and simultaneously for a lot of molecules. There's different algorithms, so there's ways for a computer program to determine C log P. Different companies sell their own versions that they say are maybe the best way to do a C log P. Fortunately, there are some free ones. One of the ones that is great is produced by Mole Inspiration Chemical Informatics. So this is a freely available one. It's on their website, and I think you can do like maybe 1,000 C log Ps a day, and then it cuts you off. So as long as you're under 1,000, you should be fine. And so we can use it in our class, and you guys will be able to determine your own C log Ps this way. Okay, and the other thing is that Mole Inspiration, they call their C log P, they call it my log P, or Mole Inspiration log P. That's just a different version of the C log P measurement. Okay, here's an example. So this is epinephrine, which is adrenaline. It's a neurotransmitter and a hormone, and it's extremely polar with the catechol, the two hydroxy groups, and also this hydroxy group and this amine. This combination of hydrogen bond donors really makes this very polar, and so it's kind of on the negative end of pretty extremely polar compounds. And this, I believe, is not orally available. I'm not 100% sure on that. Another molecule, aspartame. And so this is NutraSweet. It's a dipeptide with phenylalanine, methyl ester, and an aspartic acid. And it's, we use it as a sweetening agent, so we don't need this really as a drug. So if it touches your tongue, it has a kind of a sweet effect. So, but we're not really using it as a drug. But it also has a very, very low C log P, or as they call it, my log P. Mi log P. Hydrocodone, which now we're getting into more orally bioavailable drugs. So this is one of the mu opioid receptor agonists. It's used as a painkiller. It's got a mi log P of 1.73, and so there's a little more greasiness to this molecule. It has polar functional groups, but it also has greasy things like the benzene and the cyclohexanes and things like that. Hydroxychloroquine, which is actually, it's one of these drugs they're considering for COVID-19 right now. It's also called Plaquenil. It's really used as an anti-malarial drug, and probably for maybe 50 years or something like that. It's very closely related to chloroquine. Chloroquine's the same thing minus the hydroxy group, and chloroquine's been around since like the 40s. And chloroquine is actually related to quinine. So quinine, which is found in like gin or tonic water and like gin and stuff like that. Quinine has a pretty complicated structure, but it's kind of similar. It's similar in some ways. It just has a different thing on the top. And quinine is definitely another good anti-malarial drug. The problem with quinine, and I wish I have this. Well, I can do my browser thing. Let's show quinine. Quinine has a similar structure to hydroxychloroquine. And quinine is a naturally occurring molecule. There it is. So it's got a methoxy group on the quinoline, and it has this kind of weird alkaloid thing on the top. And there's an interesting story in how this was actually used to treat malaria kind of around World War II, but they couldn't produce it in large enough amounts to actually be used as a anti-malarial drug. And so chloroquine, which is just minus the OH, that was actually created to kind of emulate some of the properties of quinine. And so that's how chloroquine and later hydroxychloroquine came to be as anti-malarial drugs. The mechanism is something about interacting with heme metabolism inside the red blood cells. I'm not going to go into that. Maybe I'll do that later. We'll see if I have time. But anyway, that's hydroxychloroquine. And it's also got a nice kind of mid-range C log P or Mi log P. Yeah. Prednisolone. So this is not the same as prednisone, but it is generally the same kind of drug. This is a steroidal anti-inflammatory drug, and used in various settings. I think maybe in skin inflammation. I think orally also. It's interesting though that as a steroid, we usually consider steroids to be very greasy. It's still got a pretty low log P, maybe close to hydrocodone or something like that. So a lot of steroids have a much higher C log P, and we'll see those in a second. Example is estrone, the female steroid hormone. It's around 3, and it has less hydroxy groups and things. So yeah, it's a little more mid-range. This could be orally bioavailable, but then just for comparison, here's cholesterol, and cholesterol is very greasy. It's a steroid with a big long greasy chain, and then the Mi log P or C log P is like 7.6. So it's like, yeah, this is like almost the extreme of a greasy molecule. And cholesterol is found in, it gets stuck into biological membranes, and it's actually a membrane component along with other things in the bilipid membrane. Okay, so let's talk about the polar surface area, PSA and TPSA. What are these things? It's another parameter, kind of like log P or C log P, that we use to determine drug likeness. So polar surface area, PSA or TPSA. I'll explain the difference in a second. What does it sound like it is? Well, a surface area, which is the area on a surface that happens to be polar. So that's a pretty good summary of what it is, actually. And so it's another useful physicochemical parameter. So physicochemical are these things related to drugs that are, it's related to solubility and polarity that we use to determine drug likeness. And it's used to predict membrane permeability, which makes sense, because if it's you have a large polar surface area, a very large polar surface area, then a molecule you would think might not transition through a membrane very readily. So it estimates the surface area of the molecule that has a polar features like polarized functional groups, like hydroxy group and ketones and things like that. Numbers range from kind of 0, which is very nonpolar, to maybe 200 to 300, which is highly polar. Drugs are kind of in the mid-range, mid to low, so it can't be extremely polar. It's got to have a little bit of lipophilicity to travel through a membrane. So it's complementary to C log P in some ways. So when we use this to determine drug likeness, it'll be kind of compared side by side. We'll do that with those methods like Lipinski rule and Weber rules, which we'll get to shortly. And fortunately, this is also determined for free using the mole inspiration tools. So we're going to use these in our own calculations shortly. So TPSA is called topological polar surface area. It's a really easy, rapid way to estimate the polar surface area. So rather than to do PSA, we'll do TPSA. So what's the difference? This just shows a random molecule. To calculate PSA usually requires us to convert a 2D structure into a three-dimensional structure and calculate, kind of work and work with a three-dimensional structure, determine a molecular surface, a three-dimensional molecular surface, and then look for the polar atoms. And then it kind of does this calculation, 53 square angstroms. I guess what TPSA does is it does the same thing, but it never converts to 3D. So it works pretty well. So it's just a very rapid way. This is not super slow, but if you're doing this times 1,000,000 molecules or 1,000 molecules, this may take a while. So TPSA basically looks for the polar functional groups, and it gives them numbers that can be added up. So this is a very simple automated process that gives you almost the same number, but essentially instantly. So it's a very, very rapid protocol. And so 53 versus around 51, yeah, this is a very much more ideal method. Okay, so generally speaking, TPSA gives us what we want. So we'll use TPSA in our measurements. Mole Inspiration, the website we'll use, does TPSA calculations very rapidly. Okay, so let's talk about the Lipinski rule of 5 versus the Weber rules for drug likeness. So drug likeness, what does that sound like? It sounds like, if we're considering a molecule, we could say, is this a drug-like molecule or not a drug-like molecule? This has been there's been a debate on how to do this, how to just make a decision, is it drug-like, is it non-drug-like? We already talked about Fusion, the HIV fusion inhibitor. That's not a drug-like molecule. Long peptides they are not going to be orally available. And even that aspartame, it's a two amino acid peptide. That's not even orally available, and the C log P is very, very low, and peptides in general are just not good drugs. Anyway, so Lipinski rule of 5 is one of the methods we can use, and Weber is going to be another one. And they just try to quickly determine the concept of drug likeness. So in drug discovery, given a chemical structure, it would be ideal to determine the likelihood that it could be orally active, right? So, if I'm making molecules at a drug company, it'd be nice to sort of determine this during the process of is this expected to be an orally active drug? It'd be really useful if we could use these easy to find parameters like C log P, TPSA. We can calculate these using a computer program very rapidly. So we're going to use them in our calculation. And a couple of the methods are the Lipinski's rule of 5. Rule of 5 means that a couple of the rules are going to use the number 5 in them. It just helps us. It's a rule of thumb. It can be easily remembered. I still have to look it up when I use it. It's but by having everything based on 5, it kind of helps a bit. There's also something called the Weber rules of likeness or drug likeness, and we'll find that there's only 2 rules. You might call them the Weber rules of 2. I don't know. People have said things like that. They're both kind of complementary. You can't really say one's better than the other. So it's good to learn them both. Okay, these are classical papers on these topics. Lipinski 2001, where this I think it was Pfizer. I think it might be Pfizer where he worked, but they proposed these rules in 2001, and Weber was another major medicinal chemist, and he proposed his own set of rules in J Medchem 2002. So both of these are really good papers if you're kind of interested in becoming a medicinal chemist. The Wikipedia page is really good too. It's a nice comprehensive discussion on the Lipinski rule of 5. It also talks about the Weber rules. It's a good resource. It's pretty easy to read, and it's factually correct. So, what are Lipinski rules of 5? Rule of 5. So it's these are the 5 rules. First one: no more than 5 hydrogen bond donors. What's a hydrogen bond donor? Well, it donates a hydrogen bond. Typically for us, that means OHs and NHs. So we look at every one of them and we add them up. Yeah, if you have more than 5, so if you have 6 or 7, then it will be a Lipinski violation, we call it. No more than 10 H bond acceptors. So 10 is 2 times 5. So yeah, the donors, the OHs and NHs, that's more of a problem in a molecule because those really decrease lipid permeability. The bond acceptors, so like just having nitrogens and oxygens in the molecule, if they do not have H's on them, that's less of a problem. So that's why if there's no more than 10 H bond acceptors, then we're fine. Molecular mass has to be less than 500 Daltons. So that's also easily calculated. These are all easily calculated, and we can either do it visibly by eyeball, or we can have a computer program tell us. And then the octanol water partition coefficient, which could be log P, C log P, or this MI log P that we're talking about, has to be less than or equal to 5. So now we see the number 5 a couple times. 5, 10, 5, 500, and 5. And the hydrogen bond acceptor count is just 2 times 5. So that's why it's called Lipinski's rule of 5. And the other thing is they say that any one violation is allowed. If there's one violation here, it's still considered, we'll call it Lipinski compliant. Lipinski compliant. But if you have more than 1 or 2 or 3 or 4 violations, we just kind of assume it's a non-drug-like molecule. And there are exceptions too. So there's no perfect rule for this, but Lipinski is a pretty widely followed set of rules. What are the Weber rules? The Weber rules of drug likeness is maybe simpler. It only has 2 rules. The 2 rules are 10 or fewer rotatable bonds. A bond in a ring is not rotatable, but if we have like heavy bonds between atoms between heavy atoms, bonds between heavy atoms that are not part of a ring, they're called a rotatable. We'll see an example in a second of a rotatable bond, and we'll count some up. The other rule is for the Weber rules, and not Lipinski. The Weber rules say that PSA cannot be greater than 140 square angstroms. And usually we'll just use TPSA because TPSA we can calculate very rapidly. Okay? And there's not really, there's only 2 rules for Weber, and so we can't say like, oh, like one violation is allowed. For Weber, they both have to be compliant. Both rules have to be in effect. So both sets of rules have exceptions, and they're still regarded as good guidelines. Often people use both rule sets. So if you read a paper, they might say, oh yeah, our drugs are compliant with the Lipinski's rule of 5, and they're also compliant with the Weber rules. So you might see that text in a paper. So, okay, cool. Oh yeah, sorry. Remember, the Wikipedia page is pretty good. Just look up the Wikipedia page for Lipinski rule of 5. Okay, so let's show some examples of these guys. Lipinski's rule of 5 and the Weber rules, or you might say the Weber rules of 2. Okay, so for our for comparison, I'm just going to have this little cheat sheet up here. I think that's very useful when we look at some real examples. Okay. So this is a molecule. I forgot. This is a cancer drug, chem477 or something like that. Anyway, so it's actually, if we look at the molecule and the Lipinski rules and the Lipinski parameters and the Weber parameters, it's actually a pretty bad drug, and it doesn't look very orally bioavailable. So the hydrogen bond donors is 7. Well, that's a Lipinski violation, right? Molecular weight's 543. Well, that's a Lipinski violation. C log P is negative 1.7, so that is not a Lipinski violation. That's okay. And it's got 12 hydrogen bond acceptors, right? Let's count all these things. Hydrogen bond donors, well, we got 1, 2, 3, 4, sorry, donors. That would be 1, 2, 3, 4, 5, 6, 7. So nitrogen has 2 of them, right? See if you can count 7, okay? And how about the hydrogen bond acceptors? Let's count those. We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Okay, so we got our 12 hydrogen bond acceptors. Molecular weight is given to us. C log P is determined. Anyway, these we have several violations. The only thing that's not a violation is the negative 1.7. Okay, this just shows a legend. Example of counting and calculations for Lipinski and Weber. Oh, doxorubicin, that's the name of the molecule. Doxorubicin, which has a very poor oral bioavailability of about 5%. So it's you take this orally and only 5% gets absorbed. So this would probably be a good candidate for intravenous administration, right? And I think it actually is. The guidelines are exceeded for all rules except the C log P. So this is, this shows the Lipinski rules working. Hydrogen bond donors are 7, molecular weights 543. C log P is okay, right? It's less than 5. But it's got 12 hydrogen bond acceptors. So cumulatively, that's 3 Lipinski violations when only 1's allowed. And for Weber, rotatable bonds is 11, and polar surface area is 206. Okay, so the rotatable bonds, we can count ourselves also. PSA is 206. That's determined by computer, and of course the cutoff is 140. So yeah, this didn't work. This kind of explains why the oral bioavailability is really bad. So it's 5%, and guidelines are exceeded for all rules except C log P. Another thing, rotatable bonds are sometimes hard to count exactly. So I actually counted 12. Let me show you how I got 12. So a rotatable bond is like a bond in the molecule that can rotate, and it's things that are not like OH though. It's maybe like oxygen to carbon or something like, or actually I see 2 here actually. Carbon to oxygen, that's 1. Oxygen to carbon, that's 2. These are rotatable. That bond is rotatable, and this bond is rotatable, right? So those are 2 rotatable bonds. That's 1, 2. Oxygen to hydrogen, these are rotatable also. I'm sorry, carbon to oxygen is. So we have 1, 2. This carbon to oxygen is a rotatable bond. It's so 1, 2, 3, 4. Then we have this one, 5, 6, 7. And then we have carbon to oxygen here. That's 8. Then we have 9, carbon to oxygen. 10 is oxygen to carbon. 11 is nitrogen to carbon. 12 and 13. I think I'm getting 13 now. I think I counted 12 the last time. Let's try that one more time. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It's only 12. This CH3 is actually that is rotatable. Yeah. It's a carbon-carbon bond, and so all of these rotatable bonds count. So I actually am getting 13, not 12, but they're counting 11. So there's I don't know how they were actually counting them. A good source is just look it up in the Weber paper, and I have that definition from the Weber paper. Rotatable bonds were defined as any single bond, not in a ring, bound to a non-terminal heavy non-hydrogen atom. So like these carbon-oxygen bonds. Excluded were amide CN bonds due to their high rotational barrier. So given what I actually counted 13 bonds, right? And I think they were mistaken here in this source. So nevertheless, it's a big number and it's above 10. So yeah, this violates the Weber rules. Okay, so I'm able to actually count 13, not 12. All right, so let's show one more example. Here's a little cheat sheet. And so this is a neuropeptide Y1 antagonist discovery project. And there's going to be two molecules, left and the right one. What we're going to find is the left molecule is kind of a poorly potent molecule, but not that bad of a drug. And then the opposite will be the case for the right molecule. So let's look at the left molecule first. The first thing is I disagree with this assessment again on the rotatable bonds. So we'll talk about that in a second. They say 6, I say 7. But the potency is sort of bad, right? Because we like drugs to be more in the nanomolar range. Micromolar is considered sort of bad potency for a drug. And but the other parameters aren't that bad. So hydrogen bond donors are 0. Well, we see that, right? There's no hydrogen bond donors. Are there any NHs, AOHs? No, there's 0 of those. Hydrogen bond acceptors, though, let's count them. I see 1, 2, 3. So there's 3 hydrogen bond acceptors. And remember the cutoffs. So under 5 hydrogen bond donors, well, we're good there. 3 hydrogen bond acceptors are less than 10, good. The molecular weight's 369, so that's kind of right where we want it for an orally bioavailable drug. And then the C log P, that's a violation. That's 5.7 versus 5. Yeah, that seems to be a Lipinski violation. But remember, we get 1 violation, so maybe that's okay. And then PSA is 17, so that's good for the Weber rules, right? PSA is 17 because the cutoff's 140, so we should be good for the PSA, polar surface area. And number of rotatable bonds, they say 6. I say it's 7. So let me tell you why I think it's 7, because it's bonds between heavy atoms. And like that, by heavy it's non-hydrogen, right? So nitrogen CH3, that's 1, right? 1, 2, that's a carbon-carbon bond. 3, that's another rotatable bond. The ring ones are not, we don't count the ring ones. Okay, so we have 3 so far. 1, 2, 3. 4, that's CC bond. 5 is the CO bond. 6 is this OC bond. And 7. There's 7. Okay, so we got our. That's why I say 7. I think the person that I got this from a textbook, and I think they were mistaken. I just disagree with them. But nevertheless, 6, 7, it's still under the Weber rules of rotatable bonds. So this should be an orally bioavailable drug according to Lipinski rule of 5 and the Weber rules, or the Weber rule of 2. Okay. So and then what they did to try to optimize the potency in this example is they did some stuff. they added an extra ring up here, and they extended this chain. They made a nitrogen, a couple carbons. They added a 6-member ring with a nitrogen on there, and guess what? The potency. Oh yeah, I disagree also with the rotatable bonds. 14. I say it's 12. I'll explain that in a second. But by doing this, they made a much more potent drug. It went from 2 micromolar down to 1 nanomolar. Wonderful, right? But now it's poorly orally available. We'll go through why using the Lipinski rules and the Weber rules. But this just shows that this is a problem in drug discovery. You might fix one problem, potency, and then create a whole bunch of other problems. So somehow this binds better to the drug target, but it's a less orally available drug. This could maybe work as an IV type drug though. Anyway, why is it bad? Well, hydrogen bond donors, it looks like now we have 1. So there we go. There's our 1 hydrogen bond donor. That is not a problem. Hydrogen bond acceptors now is 6. 1, 2, 3, 4, 5, 6. The ketone also. 1, 2, 3, 4, 5, 6. Okay, so those aren't a problem. Those aren't Lipinski violations. The molecular weight 591, that's a Lipinski violation. Log P now, C log P, or this might be experimental. I'm not sure if it's C log P or normal log P, but it is now 7.3, so that's way above the cutoff. That's almost as greasy as cholesterol. Remember cholesterol? So this is a very greasy molecule. A little surprising that the C log P is so high. PSA is good for Weber, but the rotatable bonds, they say 14, I say 12. Nevertheless, it's still above the cutoff, which is 10, right? So this violates Lipinski rules and Weber rules for drug likeness. Let me rationalize why I say 12 rotatable bonds. Whoops, let's go back. Okay, so NH does not count because it's nitrogen to hydrogen, but this CC bond counts. CC bond has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that's how I get 12. I think that's right. I don't know where they're getting 14 bonds from. Maybe they're counting the nitrogen NH, but that does not count though. Okay. Anyway, I think it's 12. All right. Okay. So next on the agenda, we're getting into the chemical informatics section and the computational tools. I got to stop tonight. It's actually 9 p.m. right now, and I'm finally finishing this lecture just because I had a lot of stuff going on today. So I'm going to continue this next time. I'm also going to expand this and add a couple more little computer tools. We are getting into some of the fun stuff. So computer tools for drug discovery, and we call that chemical informatics, and some computational tools. We're going to get into something called SMILES, which is a text-based representation of chemical structure, and a couple other tools. Okay, so have a great night, and I will, I guess on Thursday, I'll continue our discussion with some of these other things.